To our BCS IBS seminar. Today we have a pleasure of hosting Dr. Clive Cenxin from National University of Singapore, and our scientific host is Dominic. Dominic, please introduce Clive to us.
Hello, it's my pleasure to introduce Clive. Clive is now a appointed research fellow at the National University of Singapore. He recently graduated with PhD at the University of Singapore, working in quantum information and quantum thermodynamics, and he did the undergrad at the same place. And today he will talk with us about irreversibility and inference, classical and quantum reverse processes via Bayesian inversion. Floor is yours, Clive.
Okay, I hope that everyone can hear me clearly. Okay, so yeah, I'm Clive. I bid you greetings from the sunny island of Singapore. Before I kick off with regard to this particular presentation, maybe I'll just say a little bit about the group that I come from. So I come from the Valerio-Scorani group at the Center for Quantum Technologies. There's the few of us, and the ones that are involved in the line of research that I'm going to be talking about today would be these few of us, Valerio and myself, Ge, Lin, and Peter. Okay, I don't know whether you can see my cursor. I hope so. Okay, and not only are we involved in these works, but of course we have some wonderful collaborators. So in particular, Francesco Buscemi, who really kicked this line of research off with my supervisor, Miqueleta from Spain, also worked on our most recent paper on this matter, and of course Dominic Safranek from the Institute of Basic Science, and who is involved in something that is adjacent to this Bayesian approach to irreversibility, these things that have to do with like observational entropies. Okay, so if something piques your interest and if you want to, I don't know, collaborate with people in Singapore or come to Singapore, please do let us know. Okay, I do want to say something before I start is that I'm not feeling very well. There's like a bug going around. So if at some point I need to pause and I need to, I don't know, cough, then I ask that you excuse me in that case. Okay, so let me just kick off. So this is how I'm going to segment this presentation. I'm basically going to talk about irreversibility, kind of lay out the groundwork. Then after that, we're going to talk about Bayesian inference. Essentially, it's going to be an answer to the things that are going to be brought up in the first segment. And after that, I'm going to talk about certain results that emerge from this. So one way to really think about it is that I'll introduce a problem, and then I'll talk about a perspective that responds to this problem and the results that emerge from adopting this kind of perspective. Okay, and the results here are going to be the stuff that are in my published work. And I'll get into each of these sections when I do get to them, but you can kind of understand these results as the essential idea is that if we understand irreversibility through a Bayesian lens, it really coheres well and lends insights into the typical quantifiers that we are already familiar with when it comes to understanding irreversibility. Okay, so with that said, let me kind of just jump right into the first section. And the way that I want to do this, okay, is to really give us a kind of qualitative framing. Okay, I'm under the impression that a lot of us here are working in condensed matter. Okay, I myself, I'm not working in these things. So, and also the fact that this is going up on YouTube. So this idea of putting a qualitative framing for why quantum information scientists would be interested in such things might be useful, right? So the way that I'll kind of introduce this thing is basically to start off from how I introduce to people what I did for my PhD. So, I just finished my PhD. Some people will come and ask, so what on earth did you do for your PhD? And this is how I tend to explain it to someone that is not a physicist or not a scientist at all. I'll say that, okay, you remember last time when you were, studying science, you probably heard of this idea that energy cannot be created or destroyed, right? That energy is always conserved, right? Then they're like, oh yeah, I remember this thing. And then I'll ask them like, okay, so refrigerators, right? Refrigerators are making things colder, right? That means I'm taking energy out, right? And then they're like, yeah, that's true. And then I'm asking like, okay, energy is conserved, right? So why can't I take all the energy that I'm taking out from my refrigerator, from the stuff I put into my refrigerator and put it in my phone? Like, why can't I do that? Why? The energy is always conserved, right? It's going somewhere. So why can't I just take out all the energy that's coming out of the Coca-Cola can and shove it into my phone? And another thing is that, okay, if energy is always conserved, then why is my government still asking me to conserve energy? The universe is already doing it for me, right? So why do I have to do that? And the tendency is that people would be like, okay, I don't really know the answer to that. Okay, and this is a very cheeky way of introducing the second law of thermodynamics, right? Okay, and which can be stated in different ways. One of the things is that you can't take out all the heat from your Coca-Cola can and shove it into your phone. This is a perpetual motion machine of the second kind. Likewise, you can't do something like spontaneously bringing heat from a cold bath to a heat bath, like taking all the energy from your Coca-Cola can and putting it into a water heater or something like that. You can't do that. And so what the second law of thermodynamics says is that you need some extra, right? If you are going to put, if you're going to extract work, if you're going to try to put stuff in your phone, you need to not only extract heat from a hot bath, but there will always be some excess heat that goes into a cold bath, right? So you can never actually break even, right? You can never get 100% thing. There's even in the most idealized case in thermodynamics, what you have is the Carnot efficiency, right? And then meanwhile, when you want to kind of refrigerate something, you actually need to put work in. So that's what second law of thermodynamics is. And whatever you deviate from Carnot efficiency when it comes to these things, that is when we say that the thermodynamic entropy is increasing, okay, with regard to that engine cycle or so on and so forth. Okay, the point here is that in thermodynamics, the notion of entropy captures all these physical prohibitions that thermodynamics does not allow or prohibits, right? And of course, us as people who are familiar with physics, we know that entropy and the notion of irreversibility are deeply related, right? Irreversibility results in entropy of production when it comes to any heat engine. There's also an entropy of mixing, right? Okay, if for those of us in quantum science, we know that there's a kind of similar relationship between unitarity and the ensuring that there's no change in entropy and so on and so forth, right? Okay, and of course, irreversibility also occurs in information theory when it comes to noise or erasure or error correction. The notion of recoverability of data and the irreversibility of some kind of channel or some kind of process also rears its head. And not only does irreversibility is important in both the realm of physics and the realm of information theory as separate ideas, but where these things meet, it tends to be related to irreversibility ultimately, right? Okay, of course, we know that notions of entropy, okay, which is deeply related to irreversibility as mentioned before, is now more fundamentally defined informationally, typically speaking, right? There's, of course, you have to mention Maxwell's Demon thought experiment, which is ultimately resolved by kind of connecting thermodynamic and information theoretic concepts, which invoke notions of irreversibility, like Landauer erasure principle and also the Slizar engine. So all this to say, what's all this qualitative stuff about? It's basically to say that irreversibility rears its head in all sorts of things, right? In foundational ideas, okay, in very intersections between fields that don't seem very related on first glance, and also in very practical matters like electrical bills, okay, essentially, right? So irreversibility rears its head in all sorts of places, okay? But even though we know that irreversibility and reversibility is important, reverse processes in general are not very well defined, right? When it comes to like, you give me any kind of fault process or fault channel, okay, there is no automatic recipe for invoking a reverse process, right? So let me kind of explain what I mean by this. And of course, one way to start is to really talk about bijective channels. Okay, let's first talk about these things. So what are bijective channels? In the context of quantum science, this will be unitary channels, but essentially these are going to be one-to-one and one-from-one kind of maps, right? And if we kind of stick to the kind of stochastic classical situation, okay, which we will do for now, okay, we can write a process like this in terms of a stochastic matrix like this. And these would be called permutation matrices, whereby essentially for every column, you just have a bunch of zeros except for a single one entry, and for every row, you have a bunch of zeros except a single one entry as well. Okay, so other examples of bijective channels in the classical sense would be things like this, all written as permutation matrices. And of course, for these matrices, they obey certain mathematical rules, but essentially, if you kind of write everything, all your stochastic possible states that go through this bijective channel in a state space, simplex, right? Essentially, when it goes through something a permutation channel or bijective channel, what you get is that the entire simplex is conserved, right? Of course, these things might be going to different points in the simplex, but the simplex itself maintains its volume, okay? And so in this case, the reverse process is very obvious. You just invert the arrows backwards, and essentially, you're just taking the inverse, which just happens to be the transpose for matrices like this. Okay, so this is unambiguous. Okay, for bijective channels, all information is preserved, so reversal is obviously inversion. So for a unitary case, you just take the adjoint, right? But in general, once you deviate even an epsilon away from this thing, you start to have a map for which the determinant is not 1, right? You have a map in which the simplex does change, okay? That the amount of points that could have resulted in some given point in the output simplex could be mapped to a larger kind of volume on the other side in that sense, okay? And of course, if you kind of take the inverse of this, you know that mathematically speaking, what will happen ultimately is that you're going to map out of the simplex. So inversion no longer becomes a valid stochastic process. You don't have an actual reverse physical process now. You just have a mathematical inversion. Okay, so the point here is that inversion is no longer a valid process once you deviate even epsilon away from the bijective case. And of course, the most extreme edition of this will be an erasure channel, whereby no matter what vector you give me, when I put this this kind of singular matrix on it, which is rank 1, okay, it's going to output the same exact vector at the end of the day. So in this case, all information is lost. Okay, the simplex is going to go to an infinitesimal point in this case. And of course, since it's singular, inversion doesn't even exist in this sense. Okay, so we have this kind of relationship between these different kinds of maps. But the important part to take note of is that once you leave the bijective territory, inversion no longer serves as a valid reverse process. And of course, when it comes to the quantum situation, whereby you have some kind of quantum process or CBTP map, or even a kind of quantum erasure channel, whereby no matter what density operator you give me, I always give you back the same density operator. It's like, say, the maximally mixed state or some Bell state. I always give you back the same thing. Then all information is lost in that sense, right?
Clive, I have a question.
Yeah.
My question is, I don't quite understand. If your determinant is not 1, but also not 0, I would think that matrix M has its inverse, and that's why I can do it. The last example is, of course, when determinant is equal to 0, then you don't have M to the minus 1 well determined. Then, of course, you lose the information. But I don't see the big difference between determinant equal to 1 and determinant not equal to 1.
Okay, so that's a great question. The point here is not that the inversion doesn't exist. Okay, it's more of that the inversion in that case will always map some stochastic states to non-stochastic states. So you will have a situation whereby you don't preserve the trace of certain trace 1 vectors in this sense. So the concern here is that you lose the mathematical inversion is not a valid physical process. Does that help with the question?
But anyway.
Okay.
What is a valid physical process then?
Yeah, so it would be a process that is stochastic in this sense, right?
If I have a vector, I can rotate it, but I also can change the length. But if I change the length by factor 2, I can increase and decrease, and I don't lose anything. And
right.
Yeah, I always can make my M as a product of matrix which is proportional to unit matrix times some constant and unitary matrix.
Right. Okay.
So I'm not losing information.
Yeah. So okay. In response to that, what I think I might say, if I'm understanding it correctly, is that we'll need to after the inversion, we get some output vector, right? That we are trying to invert, and that vector might have some negativity. It might have some kind of, it might not preserve the trace, And then after that, we do some kind of post-processing. We just do something about it, and then we make it physical. The thing is that my intuition, okay, is that it's going to be really dependent. It's going to be dependent on what vector comes out of it. And I think it will then lose things like linearity or something like this. So it's all these different conditions coming together to make it such that we can call it a physical state. So we want to keep a CPTP map, CPTP, for example, right? And we want to keep a stochastic matrix, some kind of protocol that we can give that is not...
CPTP.
Sorry?
CPTP, what is it? You throw the term to us, and some of us, I'm
okay.
sure, don't understand it.
All right. So completely positive trace preserving. Yeah. Okay. Basically a map that is linear. Okay. That is completely positive. That essentially there's kind of mathematical ways of explaining it, but if you kind of dilate it to a certain space, when you throw in a kind of positive thing, a positive state, it'll always come out positive no matter how much you kind of dilate it to a bigger space, kind of looking up to a bigger space. And finally, when it comes to trace preserving, it means that it preserves the kind of the sum of the diagonal entries of the density operators there. Okay. Does that help with the questions?
So, determinant being less than 1 somehow implies that the trace is not preserved, or like the positivity is lost, or both. What do you?
Yeah. In general, that will be the case. I think that I'm not very sure about exactly when. I think it really depends on the matrix as well. Okay, that's my intuition. But what is for sure is that once you are not a determinant 1 situation, you will map some states that belong inside a stochastic simplex out of that stochastic simplex. Yeah. Okay. All right. If it's okay, I will continue on this point. Please stop me at any point in time. I apologize that sometimes I make some assumptions that does not hold. So hopefully, as I go along, things will become clearer as we move forward. Okay. The basic idea, as you guys have already caught, is that if we can only come out with reverse process, say the inversion of some kind of bijective channels, then we won't really learn much about irreversibility, right? Because that is the case whereby there is no irreversibility. So it would be very nice if there was some kind of protocol that we can kind of invoke notions of kind of inversion that is not merely mathematical inversion, right? That a kind of reverse process can always be invoked so that we might learn some new things about irreversibility. And with that, we might want to kind of essentially take inspiration from the way that certain papers have suggested that maybe we might need to think of reversal not just in terms of the physical process itself, but something to do with information. So things like Maxwell's demon, Landau erasure, and things like that might be relevant to understanding the spirit of this sort of move. And with regard to this particular statistician and mathematician Satoshi Watanabe, he suggested that one way to look at conditional probability in physics and reverse processes is through Bayesian inversion, essentially, Bayesian inference. So with that, let me just kind of remind you guys about what Bayesian inference is. And so I think the sort of base rule that we are most familiar with might be called the Wikipedia version, okay, which looks like in this form. I think we're all familiar with this one. But what Satoshi Watanabe really emphasized was the role of the prior, that even if I was given some kind of conditional probability of an event A happening a given event B, okay, the Bayesian inversion of this of the inverse of this event B given event A is dependent on the prior that would be invoked here, PB, right? And so in general, if this is a different prior that's invoked, the conditional probability on this side is going to be different, right? Okay, so the way that we note it in our papers is as follows, okay, that it's really to emphasize that we're talking about forward maps here, not just mere conditional probability. So if I had a forward map phi that maps initial states I to final states F, and I want to get some kind of inverse of this phi hat gamma that maps final states F to initial states I, then I will need to invoke some reference prior gamma. Okay, and the thing in the denominator is something that you can get from just phi and gamma. It's just the propagation of the distribution through phi. And one thing I need to emphasize a lot is that this will keep coming up is the role of the reference prior here. That this reference prior is in general going to determine how this reverse process or this retrodiction map looks like. And what this reference prior essentially is a kind of like our best current guess in that sense. Okay, so just so that we are all on the same page, let me just talk about a kind of familiar example. So in the case of a virus self-test, this would be a kind of physical mechanism, right, essentially. So you're sick, or maybe you're not sick, and you take a glob of yourself, you put it into this device, and then it propagates to some positive result or some negative result, right? And of course, virus self-tests are not bijective. Okay, there's a possibility of getting a true positive, there's a possibility of getting a false positive, right? So let's say that I take the test and I find that I have a positive result, right? Okay. But the issue is that I'm not interested in whether I get a positive result. The thing I'm interested in is whether I'm sick, right? So these conditional probabilities here that propagate towards whether I get a positive result is not really what I'm thinking of, right? What I'm actually thinking of is I'm actually doing some kind of Bayesian inversion here, right? Given that I have a positive result, how likely am I sick? And notice that then I need to invoke some kind of reference prior, right? And maybe I didn't really think I'm sick, like someone asked me to take the virus test, virus test, and I took the test and I got a positive result, and maybe I think that maybe it's 0.1% that I'm sick. Now I look at the test and I start to think that maybe I'm really sick, right? Maybe now it's like a 0.4, right? I don't know whether you have been in a situation that you really don't know, you really want to be sure, and then you take another test, right? And what you're doing really here is you're updating your prior. You then feed back the prior back into this particular term here, and you then update your prior one more time. And if you get a positive result again, then you will be even more convinced that you're sick. And of course, there's some interesting intuitions. If you're completely unbiased, if you think that it's half and half that you are sick or healthy, then as long as it's the true positive is more than, the probability of a true positive is more than that of a false positive, then you are going to be more convinced than you're not, right? But of course, if you're a cult leader and you think that you're the second coming of Christ or something, that you can never get sick, you're going to be forever healthy forever, then you will never, no matter what test it is, you will always think that, I don't know, COVID's not real or something like that, right? So this keeps everything stochastic, right? And it is fully general, and it does feature very nice intuitions like the ones that I just mentioned before. And so this is Bayes' rule. Okay, and once again, I emphasize the role of the reference prior. There are some typical choices of the reference prior. There's the I don't know anything prior, which is the uniform distribution. And of course, there's steady state, which is probably more common in the context of stochastic thermodynamics and things like that. With regard to the quantum side of things, we have a very, very important object here from Petz, the Hungarian mathematician. And there the way that he derived this had to do with some kind of relative entropies. Okay, but ultimately, this Petz recovery map has now been seen as a kind of quantum analog to classical Bayes' rule. Okay, and there's a lot of things going on, but one thing that I will just emphasize is that now the reference prior becomes a reference density operator, and you can think of it as our best quantum theoretic guess. Okay, and another thing you can note is just by looking at it, you'll notice some structural interesting features, right? For example, the posterior term, the propagated term, is lying on the denominator for both sides. Then we have the reference state term as the numerator term. And then, of course, there's this kind of adjoint relationship between IF and FI that is captured here with regard to the adjoint of the forward map. And of course, if you kind of concatenate these things as a kind of decomposition of maps, you will see that they are actually acting at the positions that you expect them to act. So there's a lot of kind of structural parallels across the board. Okay, so let me just kind of apply these things to the things that we have already seen. How does Bayes' rule deal with the stuff that we have went through just now? Okay, with regard to the bijective channel, you'll notice that if you apply Bayes' rule to it, you have a situation whereby you do recover exactly what you would expect to recover, which is that the Bayes inversion of every bijective channel is transpose, is its inverse, right? So this is also if and only if. So if and only if the channel is bijective, then the reverse channel is independent of the reference prior and bijective. This one of the the reverse channel is just the inversion. So these properties is one of the first results that we found in this line of research. And with regard to the erasure channel, how does the Bayes rule deal with this thing? So what it gives us is something very interesting, is that if you apply Bayes inversion on an erasure channel, what you get is an erasure channel. In particular, an erasure channel that wipes to the reference prior, okay? Which makes a lot of sense, right? Because essentially Bayes rule is telling you that the forward map is useless. Like you have wiped out all the information, just go to your best guess. And it actually reflects this mathematically. And of course, on the general level, it depends on both, right? So on the bijective side, because all information is preserved, you don't need your prior. You don't need it. And this is if and only if. Erasure, it only depends on your prior, right? And for the general channel, it depends on both. And so you notice that this relationship between the increase of irreversibility and what you might call like a role of subjectivity or dependence of a reference prior. And this is the same for the Petz map. These are all if and only if as well. And it can be seen in both the paper and probably more in depth in my thesis if you're interested. Okay, so all this to say that Bayes rule and the Petz map can serve as generalized recipes for the reverse process, whereby Bayes rule is the classical side of things and the Petz map is the quantum side of things. And this recovers some expected interplay between the prior information as the reference state or reference distribution and irreversibility on the map, or either it's the quantum map or a classical map. Okay, so with this, let me kind of just jump right into 3 snapshots if we kind of see things through this sort of lens, now that we have kind of put out this landscape or this theater to understand these things. Okay, so the first one I'm going to go through is this quasi-probability representations of the Petz recovery map. So I'll try to explain what I mean by this. So I've already alluded to how Bayes rule and the Petz recovery map have... Yes?
We have a question.
Yeah.
Just a small query regarding the Petz recovery map that you described. You described the forward process. So when we are trying to do the inverse or the reverse in your case, what do you mean by forward process then?
It would be some kind of quantum channel in which you are trying to get the reverse counterpart of. Does that make sense? So it's just some quantum channel.
Okay, but
yeah.
So it's a reverse or some kind of inverse of that channel in time, or like you are
yeah. You can kind of think about it that way, yeah. So a Petz recovery map is a kind of so whatever Bayes rule is in the classical sense, the Petz recovery map, according to many physicists and information theorists, that the Petz recovery map plays the exact same role. That it essentially gives you like an update for whatever initial state you thought you had, given that you have some now some output and you have some characterized understanding of the channel for which that input went through. So one thing to take note of is that the Petz recovery map only makes sense if you have fully characterized the channel. Yeah, then you are able to invoke a Petz recovery map. It's not something that you are going to do channel tomography with or something like that. Yeah.
Sorry, by fully characterization, you mean that I have all the cross operators that are describing the channel and everything? Is that what you mean by that?
Yes. So let's say that I have a bunch of cross operators that define a channel, right? How those cross operators will appear inside the Petz recovery map is in firstly the adjoint over here, and also in the definition of the posterior term. So one way to look at it is like this. So the cross operators are going to appear here, right? And the cross operators are going to appear here also. But of course, you know that we are going to put an adjoint on those cross operators, and you become unito and everything. Okay, does that answer the question?
Okay. Yeah.
Okay, thank you. Okay, so the issue here is that there was this idea of okay, so if the Petz recovery map really is a kind of quantum Bayesian inference, it would be nice if we could kind of compare them in the same language, right? Because for Bayes rule, we can write it as a kind of bunch of stochastic matrices. that's fine, that acts on vectors. But of course, the Petz recovery map is a bunch of channels or super operators acting on density operators, right? So the question was, can we get quantum theory to speak in matrices and vectors? And then so that we can kind of compare it better and almost kind of see what's the difference between quantum Bayesian inference and classical Bayesian inference in that sense. And the answer is that, yes, we can have a way of explaining the Petz recovery map and quantum theoretic objects in terms of something that is more akin to matrices and stochastic matrices. And these are called quasi-probability representations. Okay, so in short, QPR. Okay, and essentially QPR are situations whereby you kind of take all your Hilbert space objects that we're more familiar with, and we kind of shove them into this dictionary. And what it produces are these quasi-stochastic vectors. So they are quasi-stochastic because they are traced, okay, when you sum all the entries of the vectors, the state vectors, like V row over here, all the entries will sum to 1. But the entries can have negativity, okay? For those of us who are more familiar with things like Wigner negativity, it's exactly this, right? So, except for, in this case, I'm talking about on a discrete level. And what we need to invoke for these QPRs are these frame and dual operators that satisfy certain isomorphisms so that they can, they satisfy certain rules so that they can ensure isomorphism between the typical Hilbert space, quantum theoretic space of things and the kind of QPR objects over there. And so these frame and dual operators are what defines the QPRs. Okay, and you have a kind of one-to-one thing. So you can do all quantum theory in these QPR objects. Okay, but what we're interested in is how does the Petz recovery map look like in these QPRs, right? So the whole paper is to get from here down to here. Yeah. So you can look at the paper for the derivation for how we reach this, but the point here is that it looks like this. And in particular, the matrices that are dependent on the reference states or state-dependent matrices have entries that look like this. Okay, so this is really opaque. What the point is to compare it to classical Bayesian inference, right? So kind of putting it side by side, you can notice certain similarities, but let's kind of massage things a little bit. So these D matrices over here are diagonal. So essentially we can just put a square root over there so that they look kind of more similar. And once you write this like this, you can kind of make the entries look more and more like each other. And one thing that you can immediately point out after you think for some time is that if the frame and dual operators are collapsed into the same basis, then you recover classical Bayesian inference. Yeah. Yes.
Like, sorry, we have a question.
Could you please explain the notations here a little bit? Like what, could you explain classical Bay? Because you were writing Bayes rule using this phi's and phi hat and so on, and then change notation somewhere and introduce these D's. Could you?
No. Okay. I apologize for that. So these, okay, so this is to, so when you encounter Bayes rule, typically you kind of see it at the entry level, right? So here I'm now writing it in terms of these matrices so that you can act on entire vectors then rather than just some given entry, right? So the way that they kind of eventually look like, if you kind of write a Bayes map given some kind of, Ford channel phi, you eventually find that in order to get the respective Bayes map of some stochastic matrix, first what you do is that you take the transpose of your original map, then you put a diagonal matrix in front of it that has all the kind of propagated terms of the reference prior gone through the phi, and you take an inverse. So it's all diagonal entries. So it's a whole bunch of zeros, and it's just diagonal on the inverse. And after that, at the end, the last thing that impacts input vector over here would be another diagonal entry with the reference prior as its entries. You can kind of try to do this by hand, and you'll find that what you'll get at the end of the day is a matrix that corresponds to the Bayesian inversion of M phi, given the reference prior gamma. Does that make sense?
So your priors go in the D gamma.
Yes, that's right. Yeah.
And this phi gamma was this sum over all these terms that was in the denominator in the.
Yeah, right? That's right. Yeah.
All right, good.
Yeah.
Okay,
yeah. So basically what we're doing here is we're trying to force it to make it look more like the kind of QPR term that we have over at the side. And as I was kind of explaining, is that the main insight here is that if you kind of make the frame operators and dual operators not quantum anymore, you kind of squeeze them down to the same orthogonal basis, what you get is classical Bayes rule. Yeah, so the point here is something like the quasi-probability representation of the Petz goes to classical Bayes rule when you neglect tomographical completeness, when you kind of forget that you're working with quantum theory and you squeeze everything down to the same orthogonal basis, what you get is classical Bayes rule. So what's the point here? The point here is to say something like, when comparing the Petz recovery map to Bayes rule through QPR, we have strong reasons to think of the Petz map as a kind of quantum generalization of Bayes rule, given what we have seen just now. So for other insights, you can see the paper, but now I'll move on to the next snapshot, okay, which is the Bayesian approach to fluctuation relations. So I'll just very quickly run through this thing. The idea here is that these objects called fluctuation relations are quite famous because you can kind of think of them as generalizations of the second law that give a kind of entropy production. And what's notable about these things is that you don't need to assume a lot of things that the kind of strong assumptions that exist or preside over thermodynamics. You don't need to assume these things like quasi-staticity and things being close to the thermodynamic limit and so on and so forth. You don't have to assume these things, but you can still make very strong average statements about thermodynamic quantities like work and free energy. And so one thing to note is that the log of these ratios between the forward and reverse statistics represent the kind of irreversible entropy production. And of course, what's very cool about these relations is that they appear in all sorts of places. So this is a rotor protein in a wet environment. You get Crookes fluctuation theorem here. You have a nanosphere over here being bombarded by photons. You get Crookes fluctuation relation. Probably the most famous one is these RNA molecules whereby they kind of like pull and they measure like the amount of work you need to use between pulling and like letting them kind of fold back, so folding and unfolding. That Crookes fluctuation relation was found in those situations also. So it's very, very interesting. That's it. When it comes to deriving, like conceptually deriving Crookes fluctuation relation, these tend to be very conceptually cumbersome. They invoke a lot of like, thermal baths, thermostats, very like Hamiltonian dissipation terms. A lot of these stuff are usually involved in these derivations. And what my supervisor and Francesco Buscemi was trying to do, and what really kicked off this whole Bayesian approach to irreversibility stuff, is that why not just try to streamline these things in the sense of starting off from merely probability theory and Bayes rule, going all the way to the end as far as you can, and then after that embedding the physics into the reference prior. Okay, and this is precisely what they do in this particular paper when it comes to Crookes fluctuation relation, characteristic equality, and even some quantum fluctuation relations like the famous one is called Tasaki-Crookes. But they do it, of course, in that case with the Petz recovery map. I won't go into this because, for one thing, I'm not involved in this paper, but let me just take note of some notable results that have to do with these things. The first thing is that one of the things that we proved in one of our papers is that if the log of the forward and reverse statistics does qualify as an entry production, which is one of the main reasons why people are interested in fluctuation relations. This is if and only if the forward process and reverse process are actually sharing a Bayesian relationship. So the Bayesian relationship is inevitable. There's always some reference prior that's going to relate these two statistics that if you want to consider it entropy production.
There is another question.
Could you go back to your Crookes fluctuation relation once more? Could you just explain what the notations are? What W is some type of what? Or what is it? What is Y?
Yeah, so why you would think, okay, so X is some initial state for the forward process, and Y is some final state, okay, for the forward process. So let's say for the RNA molecule situation, it's like the folded one, okay, and then the unfolded, right, okay. So you apply some work to kind of like unfold the thing, and then you plot a graph with it essentially, and you plot it against some measure of
temperature.
Yeah, you're gonna okay. So
But the whole thing will depend on how you define your work, how you define your temperature,
Yes.
how you
So-
define your frequency.
Very good. Yeah. So, okay, what they do is that essentially they take this, okay, so these statistics are things that they can find, right? They basically apply some work. They're gonna take the RNA molecule from the folded state to the unfolded state, okay? And then they're gonna do this many, many times. Sometimes it's gonna give you a certain degree of work, maybe like, let's just say 10, okay? And then after that, sometimes it gives 8 because it's in a wet environment. There's some kind of stochastic context, right? Some kind of buff around it. Sometimes it helps, sometimes it doesn't in that sense, right? So there's going to be a lot of these statistics, and they do the opposite also. And they also take this reverse statistics. So if you were kind of taking it from a folded state to an unfolded state, now we take from the unfolded state to the folded state, right? And likewise, you also take these statistics, right? And then after that, you plot the log of these statistics against the work. And what you'll find is that the y-intercept, okay, the intercept of this thing, on the vertical intercept, is going to correspond to the free energy, and then the gradient is going to give you the inverse temperature. That's the point here.
What free energy is that?
Sorry?
What free energy is that? Is that
The
Helmholtz
free energy that characterizes, basically the free energy that can be extracted from the system. Yeah.
I see.
So-
essentially just fit it with the log, and then whatever is the intercept, you call it some sort of a free energy. Is that?
Yeah.
correct?
So according to Crookes fluctuation relation, what you will have plotted as the given, okay, so what you collect as experimentalist is the statistics, and you also have the measures of work, right? You don't actually measure the free energy directly. You plot the graph, then you get the intercept, that is your free energy according to Crookes fluctuation relation. Yeah.
All
I
right.
hope that makes sense. Okay.
Yeah.
Okay. Yeah. So okay, another thing is that so the point of these things is just some notable results that are related to these things. Okay. Another thing is that the assumptions about detailed balance and steady state, basically some physical assumptions that are usually invoked in a lot of these conceptually cumbersome, more conventional methods of deriving these fluctuation relations can be removed if you kind of invoke Bayes' rule in some way. And finally, so this is something related to the question that was just asked, and this is, I'm going to say it's kind of a joke, okay? We gave it to a high school student, we didn't think that it was going to go anywhere. But basically, we were asking a question like, okay, so if the idea that Valerio and Buscemi had was correct, that you can kind of understand fluctuation relations on a purely kind of probabilistic theory method, and only invoke the physics with regard to the reference prior at the end of day or whatever, okay, then could we find fluctuation relations out in the wild in non-physics context? And what we did is that, okay, so all we need is some definition of work, some kind of target system that is performing some kind of protocol in a stochastic environment, right? And essentially what we did is that we tried to do this for the game Uno, okay? That essentially the system is some player, and now the thermodynamic buff is the deck and the other players, which is fun because you can call your friends a thermal buff or something like that, non-Markovian memory or something like that. So, but the point here is that we did this thing with regard to some definition of work, with regard to some, and with regard to some definition of the forward and reverse process, and we were able to plot a very Crookes-like behavior for that thing. And then, of course, once the Crookes-like behavior appeared, which we didn't expect at all, okay, we started asking like, okay, why is this the case? And we realized that it had a lot to do with how Uno is a lot like a random walk. Okay, so if you are interested, you can look at the archive paper. The point here is that there's a possibility for cross-pollination through these different fields. Okay, so all this to say, okay, that the Bayesian approach to fluctuation relations in some sense requires less physical assumptions. It bridges fields, for example, game theory and stochastic thermodynamics, and furthermore, it's necessarily present. Okay, my last snapshot before I close, okay, and it has to do with dilations. Okay, so what's the point here? Okay, so let's consider Brownian motion. Okay, we have some Brownian particle that's kind of wobbling, and of course the trajectories that these particles can take are not deterministic, right? In general, it's going to be not something that you can predict. But of course, we know that even though it appears stochastic, what, at least according to like classical mechanics and atomic theory, is that what's really happening is that it's in some kind of environment, and it's being bombarded by some molecules, right? And if I had a characterization of these molecules, the environment around it, and I had a characterization of the reversible dynamics, the classical dynamics that are determining these things, then I could, predict in principle exactly where these particles will go. What's happening is that I am tracing out the environment. I don't know the environment, right? So essentially, the point here is that everything that appears to be stochastic and random can always be understood as an adding of an environment, okay, that you're not monitoring, going through some kind of bijective dynamics, and after that tracing out to the environment. Okay, so and of course the one that we're more familiar with is unitary dilations, or if the ancillary system is a pure state, it will be a Stein spring dilation, right? So then once I put this out to you guys that every stochastic process can be dilated, then you might immediately ask, then Clive, why do I need Bayes' rule, right? If dilations can give me reversible dynamics, then why can't I just dilate the thing? Okay, understand it as a dilation. I reverse the global dynamics, which doesn't need a reference prior, remember? And then after that, I trace away the environment. Why can't I just do this to get a general protocol for reverse process without Bayesian stuff coming in? Okay, if you try to do this, what you'll find is that this is precisely Bayes' rule. Okay, what do I mean by this? Let me once again consider a classical case. So the forward process can always be understood as as follows: adding environment, reversible dynamics, tracing out the environment. So how about the reverse process? Well, of course you need to trace out the environment once more, so you can get a reverse process on the target space. Okay, but and of course another thing that's unambiguous is the inversion on the bijective dynamics, right? The question is, what do you add as the environment for this situation? Okay, and if you kind of think about it, you realize that the environment you should add is the output environment after the environment has gone through the reversible dynamics, right? And in general, this reversible dynamics is going to correlate, okay, the environment to the initial target system. Okay, so you write it something like this. So essentially, it's going to be the joint state, okay, that the environment and the initial target system goes through, and after that you kind of condition it on the target system after that. And what you'll find is that after you enforce the typical things, this precisely Bayes' rule with this initial state that the environment is correlating with, acting as the reference prior. So the equivalence really comes from acknowledging that there's going to be correlations formed between when you make the environment go through the bijective dynamics alongside the target system. Okay, and so one way to kind of look at this is through a channel concatenation of maps. Okay, whereby you have this thing called assignment map. Okay, this is essentially the same thing as what I'm saying just now, except now I'm doing it on the full level rather than the entry level. Okay, and the reverse process, in order to take into account the correlations, how you're going to add in the beta hat B prime given A prime thing, is using this assignment map that has the joint posterior state as the object here. And you'll find that this is precisely the Bayesian inverse of the forward channel. And you have a corresponding thing to the assignment map in the quantum case called a quantum assignment map, which of course looks like this, okay? Looks much more complicated, but essentially the thing is the same. It's an object that takes into account the propagated correlations that go on from the unitary dynamics. And what you'll find is that when you account for these, the role of these correlations, you will also get exactly the Petz map of the forward process. And so a question that we immediately started to ask is, okay, all the part that deals with the correlations is the part that is extremely, extremely difficult. There are certain papers that establish how difficult, computationally speaking, it is to implement the Petz Recovery Map, okay? And it has a lot to do with this particular object that begins the Petz map in that sense, okay, which is the one that accounts for these correlations. And the question that we asked is, when are these reverse maps easy? When is it easy to implement the Petz map? Okay, when is it that I don't need to account for correlations and I kind of just throw in an uncorrelated ancillary system and I reverse the same unitary dynamics that define the unitary dilation of that channel, and then I trace out the environment. When can I do this? Okay, and we call these things tabletop time reversible situations. When the dilation is tabletop time reversible is when the Petz map can be implemented with regard to some reference prior in a very, very simple way, that it kind of just looks like us inverting the unitary dynamics and adding an uncorrelated kind of product ancillary system. And of course, a very special class of these things is a kind of object, a set of operations that is quite famous in quantum thermodynamics, okay, called thermal operations. And it will be a situation whereby beta prime and beta are exactly the same thing. And so the very obvious way that tabletop reversibility will be fulfilled, when can I not take into account the propagation of correlations is when correlations are not propagated, for example, right? And so this would be what we call product preserving scenarios, whereby the reference prior and the ancillary system going through the unitary process creates no correlations, okay, product to product in that sense. This will always ensure tabletop reversibility. Okay, so let me conclude. In the paper, we talk about general relationships between several sets or families of scenarios that relate, like, say, thermal operations and tabletop reversible things and so on and so forth. We also had a lot of interest in just the case of 2-qubit unitaries, whereby we did a lot of parametric characterization of these product preserving scenarios. But I think the most interesting thing that I want to note is that while product preservation implies tabletop reversibility, the opposite doesn't hold. Okay, what does that mean? It means that there will be situations whereby that correlations are propagated, but you don't have to take into account when it comes to the Bayesian inversion of the thing, which was quite surprising. Okay, the intuition is that no matter what, as long as correlations are propagated, you must take them into account. It turns out that there's an exclusion for this, and we don't know why. We have found certain things in the wild, but we can't consolidate what is the common reason for this. So there's more work needed here. Okay, so all this to say that the Bayesian approach to irreversibility is equivalent to the dilations or open systems approach to irreversibility due to the role of correlations. Okay, let me conclude. So irreversibility is crucial in many fields. Bayesian tools in Bayes' rule in the classical case and the Petz Recovery Map in the quantum case offer a general recipe for defining reverse processes. This approach coheres with the dilations and fluctuation relations approach, and it lends insights to both of them and into the generalization of Bayes' rule into the quantum regime, as we've seen with the QPR of the Petz. Okay, so there's a lot of avenue for future work, and a lot of this is ongoing. For instance, I mentioned the kind of role between irreversibility and the kind of dependence of reverse channels on the reference prior. It will be good if we can establish this relationship more quantitatively and more analytically. Fluctuation relations for non-physics context is the situation with the card game thing that was a very special and strange project. And after that, there was the applying of Petz to non-Markovian concatenations that's possible. And the last thing that I mentioned just now, which is the exclusion between tabletop reversibility and product preservation. Like, when is it the case that even though correlations are postulated between our reference prior and the environment, can we still implement a Bayesian inverse that doesn't account for these correlations? Okay, so with that, I thank you for your very kind attention, and we can go on to questions. Thank you.
Thank you, Clive. Do we have any?
I have a question.
Mm-hmm.
If you have a quantum channel that you can write in a lim platform, is that process tabletop reversible, or like what you said, what you mentioned in your diagram? Is reversible, that process? Can be reversible?
Okay, so I'm not really good with all this Limbardian dynamic stuff, but okay, so I'm going to tell you my intuition, if I understand your question correctly. I think that if you want to get a tabletop reversible thing, when it comes to a concatenation of channels, like some Limbardian dynamics that goes on like in continuous time, for example, then I think it's the case that my intuition, okay, it's only the case that you will have such a tabletop reversible equivalent for the Limbardian situation if it's a thermal operation. Yeah, that essentially beta prime and beta are the same thing. So you just kind of keep on doing it over and over again. Yeah. So you kind of trace things back using the tabletop reversible situation. But that has a lot to do with the fact that there are no correlations being formed between the ancillary system and the target system. Yeah. So that's my intuition for that. If you're interested in this thing, I would recommend a paper by Kwon from, I forgot what university. I think it's Seoul. Yeah, I can kind of talk to Dominic about this, but there are already people that are working on applying the Petz Recovery Map into more Limbladian situations, and their results are very interesting. It's just that I can't tell you exactly what they are off the top of my head right now. Yeah.
Okay, and another question is, if I have a typical map, I have the global unitary that involves the system and the environment. With that, I can already construct the tabletop reversible process.
So you're saying that, is this like a thing that you're implementing over and over again? And do you actually trace out the environment at every step? Which one is that the case?
That I have the unitary that involves the system and the environment.
Yeah.
And yes, I am tracing out the environment at any time step.
Yeah. Okay, so in that case, it may not necessarily be tabletop reversible, right? If what you mean by a reverse channel is the Petz Recovery Map. If you want to implement a Petz Recovery Map, it's not necessarily going to be tabletop reversible. In fact, tabletop reversibility is quite a specific scenario that for example, the most typical scenario is that the unitary dynamics, the global dynamics, does not create correlations between the target and the ancillary system. If that's the case, then it's tabletop reversible. But if that's not the case, then in general, it's not going to be tabletop reversible. You are going to need a different kind of dilation to implement the Petz recovery map of that process.
Okay, thank you.
Yeah.
So I have a question about those games. What was the channel in the Uno game scenario? Because when you play some game, there's usually some agency, right?
Yeah.
They win the game. So what's the channel? What's the reverse channel there?
Yeah. Okay. So I haven't looked at this paper for quite some time, but let me just try to remember. I think my understanding of it still is probably accurate. Okay. So what is the forward and reverse channel? Right. That's really the question here, because essentially when it comes to these Crookes fluctuation relations, okay, let me try to bring it up so that we can have something to look at. Okay. Is that we need to define the forward and reverse situation, and we need to define the work as well, right? Okay. And then once you define these two guys, right, then you can, in principle, you can plot the graph, right? So you just have to define these things, right? So what was the thing that we defined? For the forward process, we made it such that the agent, okay, which is playing this game, okay, which is a card shedding game, right? He is playing is a certain protocol that is quite effective, okay, that wins that there's a kind of statistical way to like see how often they win, okay. So for example, it employs certain strategies. For example, okay, for those of you who know the game, there's these things called wild cards, right, that you can like basically put down and you can determine the next suit that needs to be played by the other players. So one thing that the forward process player would play is that they will keep the wild card until they must play it. So this is good because it basically prevents them from drawing cards, which makes them more effective as winners, right? For the reverse process, we do the opposite of this. Once they get a wild card, they immediately play it. So you can kind of think of it. So what's my point? My point here is that the forward process is someone that is playing the game very effectively, and the reverse process, to some extent, is someone that is playing the game in an ineffective way. Okay. Essentially, you're taking the forward and reverse process in a sense that whatever protocol the forward process takes, the reverse process kind of inverts this logically, right? So, okay, then what is work? work, we defined it as the amount of deck interactions. So notice that it does fluctuate, right? So if, and what is the X and Y? The X and Y is the hand that they have. So let's say that my X is 5 and I'm going to a Y of 7. Okay, so I start with a hand of 5 cards. How many deck interactions do I have to go through to reach 7? In general, it's not going to be just 2, right? You might put down a card, and then after that you have to draw a card, and then you put down 2 cards, and then you draw 3 cards, and so on and so forth. So there's a fluctuation there. And what was very interesting is that given these things, taking the log of the statistics that we then get, there are regimes that is very crooks-like, and there are certain regimes that are not crooks-like. For instance, there tends to be a curve at the start of the graph, and then after that it becomes linear, and then it tethers off. Yeah. And the reason why is because, and this is something we show in the paper, is that actually if you have a random walk, you automatically fulfill crooks. Okay, I forgot under what definitions, but a random walk is one way that you can fulfill crooks. And in a big sense, Uno is like a random walk, except that it's a finite random walk, right? You can't get -1 hand size, right? You stop at 0, you stop at 1, right? So that's why at the start of the graph, you have non-crooks-like behavior, and after it becomes crooks-like because it becomes more like a random walk. Yeah. Okay, I've said a lot of things for this very quirky project, but I hope that answers the question.
Yeah, thank you.
I have a question. So could you remind us this Petz recovery map, or this is a quantum channel, meaning is it CPTP?
Yeah.
And also, it's also bijective or not?
No, it's not bijective. It's bijective if and only if the fault channel is bijective. Was the question whether the Petz recovery map is CPTP?
Yeah.
Yeah. So in general, it is, okay, except, okay, it can actually become trace decreasing if you have rank deficient posteriors. Okay. So which is basically a whole thing, but if you notice, actually Bayes' rule is also can actually have issues if you have singularities in your denominator, right? So let me try to find a good slide so that we can look at this. Let's see this guy. Okay, so notice that if your posterior, right? Your propagated term over here, your posterior distribution, in the denominator term, if it's a 0, you're going to have problems, right? You're going to have very serious problems. Likewise, the same thing happens for Petz recovery map, right? Once you have some rank deficient posterior states, there's going to be issues in defining a thing. Okay, so in my thesis, I actually spent quite a few pages coming up with a way to explain why this is not a very serious conceptual pathology, and how to mitigate it if we do have situations whereby there's these rank deficient posteriors. Essentially, you can add a kind of infinitesimal term and attach it to the fault map in order to prevent these things from happening. But what I will say, and this is argued in my thesis more elaborately and more succinctly, is that the reason why, the only time for which the Petz recovery map is not trace preserving is when there's some kind of contradiction between your reference prior, the fault map, and also the input that you are entering into the Petz recovery map. So my point here is that the Petz recovery map is CPTP for logically consistent scenarios. Yeah.
And so just to maybe understand this this slide more layman's term. So you just said that this Petz recovery map is not bijective, right?
It's not bijective in general, yes.
If I try to make the analogy with Bayes' theorem, we have certain results, and these results are these gamma matrices, which are the density matrices. This is what you have, right? And from here, you are trying to obtain what original density matrix gave you this gamma density matrix, right?
Okay. Actually, the thing that you have, the output that you're trying to perform the Petz recovery map on, is the thing that you act on. So it's actually the dot over here.
I see.
This the input. So it's like kind of the thing that you're trying to retrodict on, which in the virus test situation, it's like me getting a positive result, right? That will be what you input in the thing. And what the gamma is your prior guess on the matter, right?
Prior guess of that particular result, right?
Yeah, the prior guess of what the initial state was that gave you this particular result.
So then what you have at the end of applying this Petz recovery map is another density matrix with probability which is given by this phi hat thing. Is that correct or not?
Can you say it again? Sorry, the mic didn't pick it up.
Right. So what I'm trying to understand is that, so the way you apply this is that you take your final result, which you put in that dot, and use the Petz recovery map. So that gives you the prior density matrix with a certain probability which you derive from the earlier Bayes rule. Is that correct or not?
One way to think about it is that after you put, okay, so what do you have at the start? You have the reference prior, right? You have some kind of guess about like how, and this guess could be that I have no guess, which is like the uniform prior, right? Okay. I have some kind of postulate, okay, about like what initial state it was, and then it goes through some kind of some channel. I don't know what the actual initial state was, but I have some guess, okay, which is my gamma. It goes through a channel E, okay, this channel E, and then after that I want to, and I get some result, okay, let's call it rho, and then I put rho into my Petz recovery map, okay, which then gives me, which depends on E and the gamma. And I will get some new density operator, right? Yeah. And this density operator, you can think of it as the updated guess on the initial state.
No, so then I'm trying to understand the last statement that you are making is that you need Bayes rule also with Petz recovery map. So I'm trying to understand where are you using Bayes rule in this whole procedure?
Okay, so like where does Bayes rule come in the Petz recovery map? Is that your question?
I'm just writing it, right? Like Bayes rule plus the Petz recovery map can serve as generalized.
Okay. So maybe let me just explain this, is that, so the Petz recovery map, if you take everything diagonal, it becomes Bayes rule, okay? So this is one of the things that Robert Speckens and Leifer and Speckens proved, okay? But what I'm saying here is not that, okay, after I do the Petz map, then I do Bayes rule or something like that, okay? It is not the case. It's more of that if I have a quantum channel, I use Bayes rule. If I have a classical channel with classical states all around, I use Bayes rule, right? So Bayes rule for classical situation, the Petz map for quantum situation. So the plus, sorry?
There is no, so in the quantum situation, you are not using Bayes rule anyway.
Yeah, I mean, you could possibly use Bayes rule if there's some classical register after that, right? So some classical register after your CPTP map, some classical register that goes on, then after you get some results, maybe you use Bayes rule there. But if you're just talking about CPTP map and a bunch of quantum states, then you use the Petz recovery map only. Yeah.
Okay, thanks.
Yeah, thank you.
Okay, we have one question.
So, sorry, I have a simple question. Like in the Brownian motion, you can you can explain it with CPTP for the diffusive motion, right? Diffusive motion of the particle in environment. So, I'm sure you can I'm not sure with this Petz map, will you able to explain that same thing? And if in which case you are able to explain that same thing, and what is the advantage with respect to that?
Okay.
Or, yeah.
Okay.
What is extra? That's what I didn't get with respect to the Brownian motion.
Okay. So, okay, maybe I'm not understanding the question well, but let me try to give my best guess of it. So, so with regard to this dilations thing, the point here is that the dissipation that is involved, say, in Brownian motion or some other process, can also be captured in a dilations approach, right, ultimately, right? Because what you're doing is that there's some kind of environment, there's some interaction, which may, I don't know, cause some exchange of some variables, and then these variables these properties get dissipated into environment because we are not monitoring the environment goes away in that sense. Okay, all we are looking at is the Brownian motion. So maybe it loses energy, whatever, right? Ultimately, the point here is that these are basically two sides of the same coin. That you are looking at it as a dissipative thing, that's fine. Okay, you kind of have a dissipation term in your Hamiltonian, but ultimately this dissipation term can always be the kind of effective dynamics can always be understood as a global dynamics with some environment that is then traced out. Yeah. So in that sense, the tracing out, not caring about the environment, not monitoring environment, is where the dissipation kind of leaks out of the target space. Does that make sense?
Yeah, sorry. So tracing out the environment, then you get this Brownian motion or diffusing motion. So if you use this map, then you can also get that motion. But what extra can you get, or what are the other conditions that you are basically you have to imply to get this map for that system?
Maybe I don't understand the question.
So you have a particle in a basically environment, and if you trace out the environment, then you get this a CPTP map, and then describe the diffusion motion of the particle, right?
After the environment and the particle has gone through a dynamics, yes.
Yes.
A global dynamics, yes, yeah.
Yeah. Now, with this, first of all, can I get this same map going through the same kind of derivation, or how do you get this map?
Oh, okay. So, okay. So you can, so one thing that is known, okay, I forgot the name of the theorem, is that every channel, every stochastic map has a multitude of dilations. In fact, there's a kind of, basically for every, you can just have a bunch of isometries on the ancillary space, right? For the bijective side and also for the system side of things. And so there's a whole zoo of possible dilations for the same stochastic channel, right? If you are asking the question of how do I get the dilation, right? Okay, there are ways to do this. There are certain recipes that you can use. For one thing, with regard to the quantum side, for example, which will then reduce to the classical side, is that for every Krauss like some kind of cross representation of the thing, there is a method of acquiring a unitary dilation or Stein-Spring dilation from there. Yeah. So is that your question about like how do you get the dilation?
Yeah, I get
okay.
it.
Okay, so I think we've taken enough of your time, and let us thank Clive for his excellent talk and answering all the questions.
Thank you for the invitation. Thank you for the time.